So today we are starting what would have been a circle unit, but we will not complete the whole unit and therefore will not test on it. But it's important to just be familiar with some of the vocabulary tied to circles, as well as some of the things that could be used to calculate measurements when circles are involved. I wish we could get more in depth because there's a lot of cool things you can do with circles and lines, but we just don't have the time to squeeze all of that in here. So our first two pages here, we're going to have a lot of definitions, but more importantly, we're going to have some visual examples to tie into them. Just so when you look at a circle and you see that it's cut into sections or things like that, you could describe what you see. It's kind of our goal here. So first off is circle. Which we may know circle when we see one, but maybe not necessarily know what it means to be a circle. So a circle is just a set of points equidistant, meaning the same distance, equidistant from a given point which is the center, so for this example here, we have a circle. We don't actually see the center, but we could assume that it's somewhere right here in the middle. And just for naming convention, I'm going to put the letter P here. We would refer to this as circle P. Now, occasionally you may see a symbol for circle. It looks kind of strange, but it's like a circle with a dot in it and then a letter after it. I don't like to use that often because, especially if you can't see that dot, some people think it's just the letter O. But occasionally, especially in like textbooks or on online programs, that's occasionally the symbol that is used to describe a circle. Next one on our list is a radius. Now this one, again, this is a word we used previously. We had it in one of our formulas for calculating the surface area of a cylinder. But the radius is a segment with endpoints at the center and on the circle. So in this diagram here, I'm going to put that center point P in there again. I'm going to draw a segment out to the edge of the circle where I'll put a second point. I'm just going to call it A. And what I've essentially created is the radius AP. Now, the radius has lots of jobs. Normally, when we describe the size of a circle, we often refer to it as either based off of its radius, or another definition we'll have here in just a moment, the diameter. That's what kind of describes how big or how small that circle actually is. Kind of gives us a frame of reference. But quite simply, a radius is just, if you were to travel from the center of that circle out to the edge, what that distance would be. Now, does it matter which direction you go in? Hopefully not, because if you refer back to the previous definition, all the points on that circle are equidistant, meaning they're all the exact same distance away from the center. That's what makes it such a unique shape. All the points that exist that are exactly that distance, that radius from that center point. Next on our list is chord. A chord is a segment with both endpoints on the circle. So the center itself doesn't play a role. So I'm just going to pick, any 2 points on the circle. Pick one right here. I'm going to call it, I don't know, J. I'm going to pick another point right here. Call it K. And then I'm going to connect those 2 points. That is referred to as a chord. So long as both endpoints are on the circle itself, it is defined as a chord. Next on our list is a diameter. Now this one's interesting because it's actually using the previous definition of a chord to define it. So a diameter is a special chord. So a chord that passes through the center. So a diameter also has its endpoints on the circle itself, but what makes it unique is that it goes right through the center as well. See if I can do this successfully. Again, I'm just choosing letters kind of at random here. The specific letters just have no specific relation to what I'm doing. It's just naming these pieces. Now, as we kind of alluded to earlier, a diameter, actually we've used this fact, a diameter is really just two radiuses, two radii, I should say, combined. Because it's the basically from the center going out in exact opposite directions to the edge of the circle creates the diameter, which is just a radius plus a radius. Or in other words, we could say that the diameter equals 2 times the radius. Or if you wanted to in reverse, a radius equals half of the diameter. Now, for the most part, all of these pieces so far have all been contained within the circle itself. The furthest away we got was to the edge of the circle, technically on the circle. This next one, secant, goes a bit beyond. So a secant, instead of a segment, it is a line that intersects the circle in exactly 2 points. So the thing about a line, it does not stop. It just keeps going forever. But if I was to draw, just kind of throw a line across this circle here, go the arrowheads on the end because it's going to keep going forever. It does end up intersecting this circle at 2 locations. Again, just kind of throwing some letters on there so they could be named. There we have a secant. Now, we could then have a debate to say, well, technically then, if you were describing the segment XY, which is on the line XY, technically the segment XY would then therefore be a chord. Yes, when a line goes through a circle intersecting at 2 points, it does then have a chord that is created in the circle itself. So there is a very strong relationship there. So that's where sometimes the confusion between a chord and a secant. They're not exactly the same, but there's a very strong relationship. Next on our list is we have a tangent. A tangent is a line that intersects the circle at exactly one point. This one's a little bit harder to get to work here, but let me see if I can do it. Let's see. Like it just barely touches it. So I'm going to call this line PR. But the point that it intersects the circle is at a very specific point, Q. Which means what it does is, it's kind of hard to imagine, but this line comes in so close, it just grazes at one exact point before it just continues to travel away from it again. Now, see if I can duplicate this. The point of tangency is the point at which the tangent line intersects the circle. So see if I can duplicate. I'm going to copy, paste, and very carefully drop it right there. So the point of tangency from our diagram up above would be Q.
It's about the same as.
Yeah, so it's the same exact diagram, but the tangent describes the line. The point of tangency describes the point where that line touches the circle. And that point is really special because that's kind of one of a kind. So that covers most of the lines and segments involved with a circle. We're now going to transition to talk about what happens when we have angles inside a circle. So the first one we have is known as a central angle, and it is defined as an angle with a vertex at the center of the circle and two sides that are radii. Radii is just the plural of radius. So to show you what I mean by that, I'm going to put my center P again right here in the middle of this circle. And I'm going to create basically just two radii, a radius in two different directions. What we form is an angle, in this case, APB. P is the vertex of that angle, which is also the center of the circle. And what we essentially create is an angle that is inscribed, inside, so to speak. in that circle centered at the center. That's a weird definition. The definition I wrote is far better than what I said. Now, actually, I used the word inscribed incorrectly. Inscribed is the next one. So central angle, the vertex is at the center. Inscribed, the vertex is moved. So for an inscribed angle, it is an angle with a vertex on the circle and two sides that are chords. So what I would do here is I'll put what seems like 3 random points, different locations on the circle, and I'm going to connect. Come on now. Please hold. I put them ironically at almost close enough positions that it thinks I'm trying to make a 45-degree angle and a horizontal line. So in this case, we have angle ACB. C is the vertex this time, but instead of being at the center of the circle, it's on the circle itself as well. Next on our list is an arc. This is a portion of the edge of the circle defined by 2 endpoints. Now, there is a symbol that's usually tied to arc. And it looks kind of like a frown from a frowning face. So using this diagram to the right here, I'm going to draw in 2 points on the circle. And I'm going to basically follow around the edge of that circle from point A to point B. Which gives me an arc. And if I were to describe that arc, I would say that I would use its endpoints. And instead of putting a little segment above it, I put the little arc symbol above it. Now, the confusing part of a circle is that if you're talking about arcs, who's to say which direction you travel? Because think about it. I could have gotten from A to B in 2 different directions. I chose the short path, but because it's a circle and it always circles back to itself anyways, I could have gone all the way around and still landed at the same point. Now, that's very important to notice because that describes 2 different arcs. And depending on which direction you go, that affects how you name them, how you identify them. So those 2 types are known as a minor arc and a major arc. So a minor arc is an arc with a measure less than 180 degrees. Now, a little note here about it. When we're defining a minor arc, we use 2 letters when naming it. I'm actually going to highlight that because that's pretty important, because it's going to cause some confusion if we don't realize the difference. So what I'm going to do here is I'm actually going to create the same exact diagram for the minor arc and the major arc. We're just going to identify different pieces. So on this top one here, I'm going to put A right here, B right here. I'm going to put a third point, C, over here, which we'll use in just a moment. But with the powers of technology, I am going to, come on now. Oh no. There we go. So in the top one, the minor arc says it's less than 180 degrees. Basically, for our purposes, we refer to that as the shorter one, because 2 endpoints can create 2 arcs, the minor arc and then a counter, the major arc that goes with it. So here I'm going to trace the shorter path from A to B, similar like we did up above, and say that I have arc AB. And the fact that I named it with 2 letters tells me that it is less than 180 degrees. Major arc, well, process of elimination is just the opposite. It's an arc with a measure greater than 180 degrees. And when we name it, instead we use 3 letters. And the reason why we put in a 3rd letter is because the endpoints are the exact same endpoints as with the minor arc. That 3rd point tells me which direction it's traveling in, which we'll see here in just a second. So again, I very deliberately made sure the points were at exactly the same locations, because now going from A to B, but in the opposite direction, I have a longer route to travel. So I'm actually going to go around. I'm going to pass through C on my way to B. Oh gosh, I'm trying to make it look prettier, but I'm making it worse. Circles are hard. So to name this, to be able to differentiate it from the minor arc right above it, we name it A, C, B. The endpoints are the same. Ooh. But it goes the opposite direction, giving us a longer path, therefore greater than 180 degrees. Because I know we haven't talked about it specifically. How many degrees is in a circle?
$360.
360. So again, if you think about it, if you ever hear someone say, you know, I spun around 360 degrees, you spin around If you go 360 degrees, you're looking at exactly the same direction. And that's because you just completed a full revolution or a full circle. A circle is 360 degrees. So if you took a minor arc and its corresponding major arc, we then know that the total should probably give us 360 degrees. Now, the last one here before we jot down a few formulas that are tied in with circles is a semicircle. And the reason why we have to cover this is because for minor arcs and major arcs, our reference was with respect to 180 degrees. A minor arc was less than 180 degrees. A major arc was more than 180 degrees. What would your guess be about a semicircle? It's exactly 180 degrees. So the way we would describe it, how it's generally created, it's an arc with endpoints on a diameter of the circle. So as Shanitha said, we'll just kind of summarize it here. Every semicircle, no matter which side or top, bottom, whatever side of the circle you're on, always equals 180 degrees. So to draw this one here, in my diagram, I'm going to put center P as just a reference point here. I'm going to draw a segment through center P, technically a diameter because the endpoints are on the circle itself. Call this diameter JL. And then because so here's the trick. Technically, you have two semicircles which make up the whole circle. So to know which side of the circle I'm on, I'm going to use a third point as well. So I'm going to use K here at the top to find semicircle JKL. Okay. So lots of vocabulary. We have some time to cover some of this vocabulary kind of in action. But unfortunately, we won't be able to use every one of these definitions to see, what they do when there's multiple of these pieces at work. But we'll do as many as we can. Last thing on this page, a couple formulas having to do with circles. First one is the area of a circle. Technically, we use this one when we did surface area. It was actually hidden in the surface area formula of a cylinder. The area of a circle equals pi times the radius squared. Ooh. Make this a little bit bigger. Pi times the radius squared. So again, for reference, R represents the radius. Second one, circumference. Technically, there are two formulas depending on what information you have. The first one, circumference, which is usually a capital C, equals 2 times pi times the radius. So again, here R represents radius. But if you think about it, there's a 2 in there, and in its own way, it's multiplying with the radius. So someone said, well, technically then 2 times the radius is just the diameter, which means you could also find the circumference by just taking pi times the diameter. Now, if you're like, I don't know if I can remember both of those, that's okay, because if you can remember at least one of them, whether you know the diameter or the radius, hopefully you can remember that the radius is just half the diameter, or the diameter is double the radius. You could then use just the same formula every single time at that point. The last one, arc length. This one's a little bit unique, probably not one you've ever seen before. So to find the arc length, I write this kind of to the left here. It equals x times capital C divided by 360. This is where x equals the degree of the arc, and capital C is the circumference. Okay. So the next page, just an opportunity to name some different parts here. We're going to name different parts based off of the parts of the circle listed there for us, or from the definitions we just previously wrote down, to classify what we have. So I don't know how to do this seamlessly. The video is going to be a little bit spotty here because it's going to be a lot of back and forth. First one on our list, LQ. How would you describe LQ? You don't know a term, just describe what it's doing. It's intersecting at only one point.
So
It's a tangent. Okay. Next one we have is WY. Looks like both of its endpoints are on the circle. It's a chord. Number 3, angle NQR. NQR. Looks like the vertex is on the circle itself.
inscribed angle.
It's an inscribed angle. What about point X?
Center.
It's a center. Okay, try to fit as many of these on here as I can. What about arc RWU? What was that? It is a major arc for 2 reasons. One, it used 3 letters to name it. But if I were to follow in that order, RWU certainly goes beyond half of that circle, which means it's greater than 180 degrees. So this would be a major arc. What about line ST?
Point of tangent.
Careful, there is a point of tangency on that line because this line is a tangent. So there is a point of tangency at R, and very interestingly enough, it's on both circles, so that's rather unique. But the line itself would be referred to as the tangent. What about segment PN?
Radius.
It's a radius, goes from the center to the edge of the circle. Angle UXY. Looks like the vertex is at the center.
Central angle.
It's a central angle. Next up, we have arc MQ.
Minor.
It would be a minor arc for two reasons. If you look at it visually, it is certainly less than half the circle, which is 180 degrees. But it's also named with just 2 points, 2 letters, which is typical of a minor arc. What about segment QN?
Diameter.
It is a diameter. So technically, if you said it was a chord, I'd say you're not wrong. But because it's a chord that also goes through the center, it very specifically is a diameter. Now I'm gonna have to go back and forth here a little bit. So next up, we have point R.
Would that be the point of tangency?
That would be a point of tangency, and it's very special, in fact, because it's not only a point of tangency of the tangent line, it's actually a point of tangency between the two circles themselves. Line UY.
Second.
Secant?
Yeah.
Okay. That's because it passes through 2 points on the circle. Next up is arc QRN. So I heard major arc and I heard semicircle. It's tempting at first to say major arc because there are 3 letters to name it, but when you look at the endpoints, Q and N, yep, QN is a diameter, which means that arc is a semicircle. Angle MPQ.
Would that be inscribed?
So inscribed, the vertex would be on the circle. This
Oh.
vertex is at the center.
It would be central.
A central angle, good. Next up is segment QR. It is a chord. Its endpoints are on the circle. Then we have angle UYR.
Inscribed.
It is an inscribed because the vertex is on the circle itself. Then we have arc WY.
Chord.
Ooh, careful, arc.
Oh.
It'd be a minor arc because it's less than 180 degrees. Segment LN. This one's rather sneaky.
Would that be the second?
It would be a secant because L and N, one of the endpoints is on the circle, but it doesn't stay within the circle. So it's not a chord. Chord would be MN. It goes beyond the circle, therefore it's a secant. Segment UX.
The radius.
UX would be a radius. Good. And then the last one is arc RUY. Semicircle. Good, because the diameter RY is the endpoints of that arc. So the last one there is a semicircle. So just squeeze them all in there. If you're watching the video, you could pause it here if you needed to. Those are all of the descriptions. Now, time to get into it. Some of these angles and arcs, let's see what we can do with them. So our next section of the notes today is going to focus primarily on central angles and the arc measures tied to those central angles. So it says here that a central angle is an angle with its vertex at the center. Shouldn't surprise us. We defined that not too long ago. The center of the circle and its two sides are radii. The sum of all central angles in a circle, so if you were to cut a circle into a bunch of angles inside, if you were to add all those angles up, guess what it would equal? Oh, careful, a whole circle.
360.
360. 360 degrees. So in the example shown there to the left, an example of a central angle would be angle ABC. Now, there's a neat trick here. The degree of the arc that is formed by the endpoints of a central angle is equal to the degree of that central angle. Now, if you think about it though, those two endpoints do create two different arcs. A minor arc, which is kind of inside that central angle, and then a major arc, which is everything outside that central angle. The relationship is describing the minor arc inside that angle. So 84 degrees is the angle ABC. So what would be the measure of arc AC? So from here to here. Give you a clue. The degree of that arc.
Is it 84?
It is 84. Now, the second one is a little bit sneakier because now it's asking for the measure of arc ADC. So that is the major arc opposite this central angle. It's going around the outside here. Same endpoints, but it is the major arc. How many degrees do you think that is?
276?
Where'd that number come from?
I subtracted 360 from 84.
I think you meant that the other way around, but I
Yeah.
understood what you meant. So subtracting 84 from the 360 total of the circle, what's remaining is the rest of that circle. So it is 276 degrees. All right, so we're going to use that information to find some arc measures and angle measures, depending on the situation, given some diagrams. So we're going to start here with number 1. What is the measure of arc JK? 21, because the central angle attached to that arc is also 21 degrees. What about the measure of angle JNM?
339.
339? Careful.
Wouldn't you take 21 away from 360?
Well, here's the thing. It's an angle. JNM is right here,
Oh, gee.
which if you think about it, MK is a diameter, which means these two angles here add up to not 360,
180.
but 180.
So we take it from 21.
Take 21 from that 180, and we should have this angle right here.
159.
We get 159 degrees. What about the measure of arc KL?
Same thing. 180. 21. 21 from 180.
So there's a couple ways to jump to that conclusion. I want to make sure that we're comfortable with how we did that, because it is 159 degrees. What I would notice though, is that angle JNM and KNL are vertical angles, which means this angle here is also 159 degrees. But being a central angle, that means the arc created by its endpoints would also be 159 degrees. Now, technically, you could have also subtracted 21 from 180 if you wanted to think about JL as a semicircle. Take away 21 degrees from that semicircle, what's left of the 180 is going to be 159 as well. So there's a few ways you could defend that answer. What about the measure of arc JKM? Trace it around so you make sure you're including everything. JKM.
Would you minus 159 from 360?
Okay, that'd be one way to do it, because if you think about this, the whole circle is 360. JKM is a major arc. We need to remove JM from 360.
201.
Taking that 159 out of the equation, we're left with 201 degrees for our major arc.
Same for the other one.
Careful, let's trace that one out. MKL. So we're going all the way around the circle except for this little arc right here. What is the length of that arc?
21.
21. So take 21 out of 360, because that's the only piece we're removing from the entire circle. We
339.
get 339. Good. I'm going to give you the answers to number 2, so I can skip to number 3. Number 2, the measure of angle UXV should be 72 degrees. Measure of arc ST is 21 degrees. Measure of arc WV is 108 degrees. The measure of arc TW is 93 degrees. And the measure of arc TVW is 267 degrees. Again, if you wanted to work through it, check those answers, please do so. I want to make sure we can look at a few more varieties here. So number 3, couple things to point out. We have an arc measure for arc FE. We also see that there's a 90-degree angle at CHD, which is also a central angle. First on our list is the measure of arc CD. What would it be?
You should take 90 away from 180.
Careful, that arc has endpoints on the central angle CHD. A central angle equals the degrees of that arc. This one would actually be 90 degrees. Next on our list is arc FD. Now this one's kind of sly because it requires us to come to a conclusion. If this was 90 degrees, can anyone tell me something about angle DHE? It is also 90 degrees, which means if this angle is 90 degrees, arc DE is 90 degrees, but we want to go from F to D. So that's the 90 plus the 34. We get 124. Next up, we have arc DCF. So it goes DCF. Well, if I'm not mistaken, that is everything other than arc FD. DCF is just taking out minor arc FD. FD was 124 degrees. What does that leave us for the rest of the circle?
You do 124 from 360.
Mm-hmm. You get 236 degrees. And then the last one is the measure of arc GDF. So G, oh goodness, G all the way around to D, all the way around to F. That one, I would argue it may be worth figuring out what GF is and just take that from 360. Well, I have another 90-degree angle in here, which means GE is 90. If you take the 34 away from 90, what does that leave you for GF?
56.
Okay. The arc we're looking for is everything but arc GF. So if you take that 56 away from 360,
304.
you're left with 304 degrees. Good. 4 is relatively similar. So I'll give you those values here so we can continue to progress. The measure of arc PQ should be 71 degrees. Measure of arc SR should be 161 degrees. The measure of arc QRT should be 199 degrees. The measure of arc PSR should be 270 degrees. And the measure of arc PS is 109 degrees.
So what time will you be here tomorrow?
Yeah, I'll still be here as early as 9.
Okay.
So next section, you're going to notice we're throwing some variables into the mix as we normally do in these situations. Make sure you're paying attention. Sometimes it's going to be asking for the variable. Sometimes it's going to be asking us to use that variable to find other measurements. So starting with number 5, we're just looking for X. X is in this expression here, representing arc RS. What can I do here? What relationship could I set up?
Would you do 15x minus 26 plus 26 equals 360?
Almost, really close, in fact. Except, so you said 15x minus 26 plus 26 equals 360, but look at how much that circle we have. That's not the whole circle. In fact, RT is a diameter, which means RST is a semicircle. So that wouldn't equal 360. It should equal 180. So 15x
Minus 26 plus 26 equals 180.
minus 26 plus 26 equals 180 degrees. Combining like terms here, I probably gave myself too much space. Negative 26 and positive 26 actually eliminate each other, leaving me with 15x equals 180. Divide both sides by 15. What do you get for x? 12. Number 6. A lot of information going on here. We're just looking for x, which is over here in this expression for arc DE. What are your thoughts?
Would you set it equal to 180 again?
Not quite. Here's what I would do if I was looking at this one. I look first at all the information it gave me. So it gave me arc DE, DH, and GF. Well, if I think of those in terms of their central angles, I notice that angle HIE, which is made up of arc DH and DE, is a vertical angle with angle FIG, which means vertical angles are always congruent. So this whole measurement here, which equals its central angle, should be congruent to this whole arc here, which is congruent to its central angle. So basically, if I was to highlight this, see if I can do it smoothly. Nope, not that smoothly. This arc and this arc should be congruent because the central angles they are attached to are vertical, therefore also congruent. So I should end up getting 18x minus 2 plus the 15-degree angle should equal 103 degrees. Combining like terms, I get 18x plus 13 equals 103. Subtract 13 from both sides. I get 18x equals 90. Divide both sides by 18. I believe I get x equals 5.
Maybe it's sort of a different way. I
Okay.
subtracted 15 before I started.
Subtracted 15 from what?
I subtracted 15 from 103.
Okay,
And then that was what I said.
that result you said equal to this expression. So that works too. Technically, instead of combining like terms, I could have subtracted the 15 from both sides, and I would have been in the exact same scenario you just described. So a different description of the same process, so to speak. Equally good though. Everybody sees those problems so differently though, it's hard to cover every possible path. Next one here, a little bit more involved because not only is it asking for X, it's also asking for some of the arc measurements. I would suggest we find X first. Similar to the last one though, if you notice that the two angles, the two arcs that have the expression in them, if you consider the central angles that they are attached to, those central angles are vertical, which means these two arcs should be congruent.
So set them both equal to each other.
Set them equal to each other, absolutely. So 10x minus 22 is going to equal 8x plus 12. So get the variables to one side. I'm going to subtract 8x from both sides. I get 2x minus 22 equals 12. Add 22 to both sides. I get 2x equals 34. And then divide both sides by 2.
17.
I get x equals 17. Now, that is one of the values that it was asking for, so I'm going to go ahead and write that over here on my answer line. But now it wants measures of those arcs. Well, if I start plugging in those values, AD is just the 8x plus 12. So if I drop 17 in for x, multiply 17 by 8, add 12 to that result, I believe I get 148.
Yep.
148 degrees for that. CD, I've got a couple ways of doing that. If you notice where CD is located, AC is a diameter, which means ADC is a semicircle, 180 degrees. We want DC, so take away the 148 out of 180.
148.
You're taking 148 from 180. So 180 minus 148. Because 148, oops, wrong tool. 148 is AD. Subtract 148 from 180, you're left with just DC. Should be 32 degrees. And then BDC, well, that looks like it's everything except arc BC. Well, as we mentioned earlier, it's how we found X, BC and AD are congruent. AD is 148. If we take 148 out of this whole circle, so minus or subtract it from 360, we should get 212 degrees. Moving right along.
Set them equal to each other on the next one.
On the next one, not quite. So I'm going to actually set this one up, then I'll let you solve the rest. Actually, we'll solve for X, and then I'll give you the answers for the rest for you to check. So this one, we wouldn't want to set them equal because these two arcs together aren't attached to vertical angles. It's actually attached to a diameter. So both of those combined should equal
360,
a semicircle
180.
is 180. So 17x minus 41 plus 5x plus 23 should equal 180. Combining like terms. I think I get 22x minus 18
Mhm.
equals 180. Add 18 to both sides. I get 22x equals 198. Divide both sides by 22.
9.
X equals 9. Using that X and working your way through the different arcs, you should get that the measure of arc JK is 68 degrees. The measure of arc MJ is 112 degrees. And the measure of arc LMK is 248 degrees. Now, for the sake of time, I'm going to give you the results for 9 because I want to take a quick look at arc length before we run out of time. So on number 9, you should get X equals 7. Arc WX is 135 degrees. Arc YW is 146 degrees. Arc YX is 79 degrees. And arc VXW is 304 degrees. All right. Our last section here has to do with arc length. We did write this formula down earlier on. But as a refresher, the arc length formula, L equals X minus C divided by 360. Now, as a quick recall, circumference C equals 2 pi r, or C equals pi times the diameter. And that's for if we need to calculate either of those measurements. Now, what this essentially means, though, if you read that statement there, the length of an arc is a portion of the circumference, which is why we find the difference of what portion of that circumference it is and figure out then what percentage of that circumference it turns out to be. That gives us our length. So in order to know that, we are going to need to know two things first. We're going to need to know the degree measure of that arc, and we're going to need to calculate the circumference of that circle. So let's give it a shot. First example here says if EB, which is a radius, is 15 centimeters, find the length of arc CD. So we're looking for this arc right here. Whoops. Okay. Well, let's make sure we have our measurements. First off, let's just go ahead and calculate our circumference. Well, it gave me the radius equals 15 centimeters. So the circumference is going to equal 2 times pi times the radius, which is 15. Now, to stay as exact as we can for as long as we can, I'm going to go ahead and say that the circumference is going to equal 30 pi for right now. The second thing that I need is X. X represented the degree measure of our arc. So I need to know how many degrees DC is. Well, if I could figure out its central angle, I would know the measure in degrees of the arc. How could I figure out this angle right here? I'll give you a clue. DB is a diameter and therefore also a line. We have 68 degrees here. How could I find what's missing right here?
68 minus 180.
Reverse that, but yes, take 68 from 180. We get
112.
112 degrees. That is the central angle, but also the degree measure of arc DC. So I could write next to this that X, which is the arc measure, or excuse me, degree measure of that arc, is 112 degrees. Well, if I take that information now and plug it into my formula, my length is going to equal 112 times, excuse me, did I say times? I feel like I've made a mistake here.
There it is.
I think I wrote down the formula wrong.
Isn't it X minus C divided by 360?
That's what I thought, but now I'm second guessing myself. I think I made a mistake somewhere. So upon further investigation, my arc length formula is wrong. It should not be x minus c, it should be x times c, which means, whew, it's gonna really screw people up watching the video. Going all the way back to here, oh. Well, I feel just silly now. I did have it right originally, the first time I wrote it down. Oh, for shame. It's x times c divided by 360. We wrote it down right the first time. I miswrote it the second time, but we're back on track. So 112 times c, which is 30 pi, divided by 360. I'm going to suggest we simplify it one step further before we grab a calculator and do it all the way. 112 times 30 gives me 3,360 pi over 360. And at that point, we're going to have to round because there's a pi in there. In my calculator, I would enter exactly that. I would do 3,360 times pi divided by 360 is going to give me 29.32. While you're still writing that down, on a side note, I feel like it's a good thing that math teachers make mistakes and are humble about it, because I think it just emphasizes the fact that it is a challenge. And because there's so many symbols and signs and numbers and everything, it is easy to mix things up. I am your evidence today. Number 11 is pretty similar, so I'm going to give you that answer if you wanted to try it on your own. I want to make sure we get at least a little variety here. Well, shoot, we're running out of time. If you try number 11, the approximate length you should end up with is 27.65 feet. Number 12, I think this will be our last one for today. I'll give you the rest of the answers in case you want to try some out on your own. But number 12 says VS, which looks like a diameter, is 12 meters. So since I have the diameter, circumference is just pi times the diameter. Or in this case, I'm just going to say pi equals 12 pi. See how flustered I've gotten now? We still need x though, which is the degree measure of the arc UT in this case. So let's pick that out of the lineup. UT is right here. Whoops. Well, if I look at this, I see a 90-degree angle with SWT, which by proxy then means angle VWT is also 90 degrees. Well, that's just it. We've got, because we also don't know angle VWU. But I could find it relatively quickly because I have 127 degrees right here. RU is a diameter. So if you take 127 from 180, we're going to get this angle right here. So what's 180 minus 127?
53.
53 degrees here. We know this whole segment is 90 degrees because its counterpart right next to it is 90 degrees. So we want what's remaining of the 90 degrees right here. So take 53 from 90, you get
37.
37 degrees. Now, what's nice is all of these angles are central angles. So the central angle measure corresponds and equals its arc measure. So UT is also 37 degrees. So X is 37 degrees. And now that I've got my head on straight for this one, the length equals X, which is the degree measure of the angle, times the circumference. I'm going to take that degree sign out, which is 12 pi all over 360. 37 times 12 gives me 444. Don't lose the pi. And then when I grab my calculator and enter it in exactly as I see it, I should get approximately 3.87 meters. Now, because we're here in crunch time, I'm going to quickly give you these other answers if you wanted to kind of try them out on your own. Number 13, you should get approximately a length of 61.21 inches. Said approximately, but then I put equals. 14, you should get that the length is approximately 109.8 yards. And number 15, if you try this one out, you should get an approximate length for the arc of about 7.62 millimeters. So where's those last four for you? Need them.
Josh,
Yes.
I'm not doing something right with my calculator.
Okay, we'll check that here in just a moment.
Okay.
I'll see if we can get some of those values to work out. All right. So yeah, that in a nutshell is a very, very, very brief, rushed introduction to lots of parts of circles, and then specifically focusing on the relationship of central angles and their corresponding arcs.